Hi there. In this video, we'll learn about piling as the most common approach to deep foundation. Specifically, we'll learn about the different types of piles based on their material, their construction methods, the methods to assess the pile load capacity, and the safety considerations in piling operations. Deep foundations are needed for structures with heavy loads or on weak, shallow soils that lack the sufficient bearing capacity. So instead of shallow spread footings, the structure can be supported on piles or caissons. Piles are more common than caissons and can be seen from regular office buildings all the way to heavy industrial buildings. A single building can have tens to hundreds of piles, where each three or more piles share a pile cap as an intermediate to distribute the load from part of the building to each pile under the cap. Deep foundation piles are also called load-bearing piles. There is another type called sheet piles, and they are mostly used to hold lateral soil load, not vertical structural load. Load-bearing piles transmit the structural load to the soil through either pile-soil side friction, bearing of the pile toe on the soil, or both bearing and friction. Based on their material, load-bearing piles can be classified into timber, concrete, steel, and composite. Concrete piles can be constructed in different approaches. So there are driven precast piles, shell cast in place, and augered cast in place piles. Let's check each pile type. Timber piles are made from continuous tree trunks that range in length between 15 and 45 feet. Timber piles enjoy the same benefits of the timber construction systems. In the US, timber is very local and available material, so no long lead times are needed to order the piles. Timber is very economical construction material compared to steel and concrete. It's easy to work with timber piles in terms of handling, driving, pile cap adjustments, and extraction. However, timber comes with its own problems as an organic natural resource. You cannot obtain low tolerances in timber piles as they are not 100% manufactured with human enforced quality controls. It's not typical to use timber piles in foundations that extend beyond their maximum lengths of around 45 feet. Also, timber doesn't have capacity to drive in tough soil formation. This is also why their capacity comes from soil friction, not from soil bearing at the pile toe end. Finally, timber piles deteriorate faster than other manufactured piles unless they are treated with preservatives that are not that environmental friendly. Precast concrete piles overcome a lot of the timber pile constraints, but they come with their own limitations. These piles are manufactured in precast plants with standard cross sections like square, octagonal, and circular. Precast piles have great resistance to chemicals and biological agents if the right concrete mix is used with the right tight quality controls. As a reinforced concrete member, precast piles provide higher bearing capacity than a timber pile. Some piles are even equipped with small jetting pipes to help over breaking the ground under the pile during the driving process. However, precast piles come with fabrication and installation challenges. Similar to timber piles, it's difficult to extend the length of the pile after it's fabricated and delivered to the site. For higher load capacities, precast piles don't become the most feasible option due to their heavy weights and increased need for large cranes to handle and drive them. These piles are fabricated off-site, so there is a lengthy process of shop drawings and submittal approvals that extend their lead time compared to other pile types. Finally, precast piles are vulnerable to damage during handling, especially if they are kind of cylinder. So to overcome this problem, another additional reinforcement is included in the pile design to account for the pile load in case of handling and rigging it. Cast-in-place concrete piles are one of the most versatile piling approaches, but it requires more concrete resources and a hefty budget. Cast-in-place concrete entails digging the pile holes and casting the concrete inside the holes after dropping the required reinforcement. The top photo shows the constructed piles extending to the ground level, while the bottom photo shows the constructed piles extending to the ground level. While the bottom photo shows the piles constructed up to the basement level inside a deep foundation deck. These piles can be excavated using two main methods, the displacement and non-displacement methods. The displacement method depends on creating the pile hole by displacing the soil within the hole. So very minimal soil spoil is created. This is done by driving a steel pipe with a closed end to the ground, displacing the soil to the side while it penetrates deeper. The void inside the steel pile receives the steel reinforcement cage and is filled with concrete. The steel pile can be extracted using a pile vibrator driver, which we will see later in this lesson. You can see that the pipe is extracted without its space, so as they are not welded strong enough. In some cases, the steel pile can be left in the ground with the concrete to create a composite pile. The displacement method requires a loose type of soil to be able to drive the steel casing easily and displace the ground around it. The non-displacement method is called auger cast-in-place concrete piling. And instead of displacing the soil is excavated and extracted using an auger and drilling buckets. The process starts by digging the surface with the auger for the maximum depth where the soil can stand by itself. Then a shallow steel casing is placed in the pile hole to support its sides for the top weak soil layers. The auger continues its pile digging with the help of a slurry mix like bentonite to support the sides of the hole. So the auger keep going down the hole to dig the soil and bring it up to the surface and dump it. This auger process is repeated until the desired pile depth is reached. In some pile designs, a special auger is used at the end to create a wider pile toe for increasing pile bearing capacity. Once the hole depth and toe are created, the reinforcement steel is dropped in the hole as one continuous cage. Then a concrete casting pipe is dropped all the way to the hole bottom and the concrete pouring starts. While progressing with the concrete pour, the concrete pipe is raised incrementally to be just below the poured concrete in the bottom. This is critical to make sure that the concrete doesn't segregate if done directly into the bentonite slurry mix. Once the concrete casing is done, the top casing is removed. Usually the pile head is jackhammered and demolished to bring the pile top to the desired foundation level. Let's watch this video to visualize auger piles construction process. Regardless of their construction methods, cast-in-place concrete piles overcome the limitations of most driven piles. The lightweight pouring case doesn't require heavy crane capacities, and it can be shipped in segments and assembled on site. This means that extreme pile lengths can be achieved, and they can be even adjusted easily for last-minute design changes. The right amount of steel reinforcement is used in this case compared to excessive reinforcement in precast concrete. There is no need for heavy cranes again, as the piles are constructed in their holes and not handled on the surface. And whole piles can be constructed with no much lead time, allowing for flexible projects with quick design changes. Cast in place still impose challenges. There is much less quality control power for the contractor when constructing these piles, as there is no reliable way to see what's happening deep there in the pile hole. This means that nicking and wasting can happen somewhere along the pile depth when the whole sides are not perfectly vertical. Cast-in-place piles are not effective in marine construction, as they cannot extend beyond the soil surface, because soil is basically acts as the formwork here. These piles can still be used in marine construction, but they require expensive coffer dams. Finally, cast-in-place piles are more pricey than other piles than other pile types, because they require a lot of more resources and operations on site, like running a slurry mix station, an additional crane, excavator, and trucks for hauling the soil, and a space also to fabricate the continuous steel cage. Steel piles can be a viable alternative to precast and timber piles, as they provide a deeper foundation depths with installation easiness. Steel piles come in two cross sections, H sections and pipes. H steel piles can be driven easily in the soil, as they cause less displacement around them, but this means their capacity is mainly achieved by their end bearing with no much contribution from friction. Steel pipe piles can be open or closed ended, and can be filled with concrete to create composite piles. Composite piles combine the benefits of using steel and concrete while still enjoying easy constructability in most of the cases. In hard soils, the piles can be constructed as precast concrete piles with a steel H-tip or a steel tube filled with concrete. In harsh machine environments, the steel pipes can be prototyped with a strong plastic layer, can be protected with a strong plastic layer, which provides the required marine protection without the need for the harsh creosote treatment. So we covered so far the load bearing. Let's cover sheet piles. Sheet piles are used usually as a temporary structure on concrete sites to create a deep excavation by creating a rigid barrier for earth and water. Sheet piles are predominantly steel with standardized sections that are driven to the ground side, to the ground side by side with the help of strong side interlocks at the end that create at the end a solid continuous wall. Except for cast-in-place concrete piles, all other pile types are driven into the soil using different pile hammer designs that utilize impact and vibratory energy to penetrate the soil, to penetrate the pile into the soil. The most intuitive way to drive a pile into the soil is to hammer it, and hammering it the old way using a heavy ram that's lifted and dropped by a crane over multiple times. The hammer weighs between 500 to 3,000 pounds, which typically means that it can have to double the weight. It can be half to double the weight of the pile itself. A pile cap or cushion is placed on the pile head to protect it from the local damage of the hammer. Hammer driving is a slow and tedious process, but it is a cheap approach with less mobilization overhead that's suitable for remote piling projects. Let's check this video of a drop hammer in action. Following the Industrial Revolution, the hammer dropping and lifting can be automated by using the steam power of the compressed air power, or the steam power or the compressed air power. This schematic shows a cross-section of the steam or air piston cylinder, which follows a very similar mechanism to the pistons we have in cars and other machines. The single acting driver uses the air or steam pressure to lift the hammer and then leave it to drop by gravity. Let's check this video of compressed air hammer in action. Pay attention to the compressed air that gets exhausted from the ram piston cylinder. In double acting steam or compressed air, the double acting stream or compressed air can be improved by using the compressed air or steam to create differential pressure in both ways, lifting and dropping the ram. This delivers more driving power with the same input of energy. Differential acting hammer is an improved design of single acting hammer that depends on recycling the pressured air or steam instead of exhausting it. This results in a faster driving process and less compressed air or steam. Diesel hammers are self-contained hammering apparatus, meaning that once you start running the hammer, it keeps going and doing its job without additional direct energy source like feeding in compressed air or steam. It works like a car engine where you just turn it on and it depends on burning fuel to release its stored chemical energy. Let's check a typical cycle of the diesel hammer. First, the piston and its position, and then release to drop under its weight. During its fall, diesel is injected into the cylinder chamber. The continued down stroke of the arm compresses the air and fuel to result in ignition. The resulting explosion drives the pile downward and the piston arm upward to repeat the cycle. Let's check the video of a diesel hammer in action. Pay attention to the smoke coming out of the hammer when the piston ram gets up and down. It's actually pretty fun to watch. Hydraulic hammers utilize the hydraulic pressure fluid instead of the air and steam to drive the piles. Similar to compressed air hammers, they can be single and double acting hydraulic hammers. There is also a hydraulic driver that's similar to car lifts. Hydraulic hammers and drivers are becoming popular as you can already utilize the hydraulic system in most heavy equipment like excavators and cranes to power the hammer or driver. Let's check this video of a hydraulic hammer in action. You can identify the hydraulic hammer by not observing any exhaust air or steam coming out of it during operation. Vibratory drivers utilize different energy approach than all the previous hammers and drivers we covered so far. This driver utilizes vibration to shake the pile with high frequency, which in turn shakes the soil to clear way for the pile to penetrate. So vibratory drivers are valid for very specific applications, namely steel piles that are driven in non-cohesive soils with high water saturation levels. We also have seen that these drivers are used to extract the steel casings used in the case of cast in place concrete piles. Let's check this video of vibratory driver in action handling and driving a steel H pile in the soil.
Looks like nothing is what it looks like. Zero everything out, and it'll drive it and keep it within a degree all the way down. This one here, I didn't get that. That option is 20,000.
Yeah.
This one right here, you drive it so far, and you can check it. If you have to, you tweak it a little bit and keep it straight. It's a little slower that way, but I didn't know that if I figured like that day will hold that for 20,000. I can have him hold that long.
What was the price of this unit?
100,000.
And it's a 50 ton?
Put something that's a little bit don't have sound like that.
Oh, that's good. So much faster.
Yeah. You turn loose, and you get it in there so far, then they'll turn it loose to the side and get on top. It's got another set of jaws on the bottom. And they drive straight to the top, and then they don't have to reposition. thing, you just don't have a lot of things over your head all.
Now there's a big question. How can we verify that the driven or bored pile provides the load capacity intended in the design? Let's cover some of the available ways to measure the pile's safe load. Some of these methods apply to driven piles, and the rest apply to all pile types. The pile driving equation is the first approach used to estimate the pile safe load. Its version appeared in 1888 article in the Engineering News, and it was afterwards updated. The shown formula is one of the latest revisions. The safe load R is a function of 5 parameters. E is the energy that's delivered by the hammer in each blow, which can be directly given or calculated as the multiplication of the hammer ram weight and its drop height. S is the average penetration of the pile in the last 6 blows. K is a coefficient of restitution, which is used to consider the dynamic impact contribution of the hammer that is increased with the weight of the pile. The heavier the pile, the more the dynamic impact. WR is the hammer ram weight. WP is the weight of the pile and any loading attachment connected to it. Static load piles can be performed by any driven or bored pile for the purpose of either investigating the soil or validating the pile capacity. In some large industrial and heavy projects, these piles are constructed before the design is performed as part of the soil investigation effort to collect field data that can be used in the foundation design. Or the same test can be performed for a pile during the construction to validate the design assumption. This test is done by constructing tension piles around the target pile and assemble a load frame on the pile head. A hydraulic jack applies the load between the frame and the test pile to impose the tension load. The frame is pulled down in place with the help of the tension piles, which obtain the resistance from the soil fraction. Dynamic load tests are performed on a driven or cast-in-place piles to confirm pile bearing capacity. The test is carried out using a pile driving analyzer, PDA, to acquire force and velocity data from the side of the pile. So it collects the data when it's subjected to a blow by a pile driving hammer or drop weight. The data is analyzed by the PDA during the test using a software called Case Pile Wave Analysis Program, or CAP-WAP, which is based on the case method capacity calculations. The CAP-WAP software gives a final report results almost in the same day of the test, including the pile shaft resistance, the toe soil resistance, the pile static load, and the deflection curve. Dynamic pile testing is relatively easy to carry out on a driven pile. On a driven pile site as it utilizes the installation hammer and requires no special pile preparation. Here are some safety precautions to consider during pile driving operations. When handling and rigging a pile, workers around the pile are under the risk of being hit by the lifted pile or getting their hands pinched or tangled with the rigging cables. So it's important to wear heavy-duty protective gloves and secure the piles with tag lines during their rigging time. Pile driving using hammers imposes more risk than vibratory drivers. For example, workers need to climb to high elevations to the pile head to replace the pile cushions or fill up the diesel for the hammering. In doing so, it's highly advisable to be aware of your surroundings, not like that worker here. Let's finally conclude this lesson with an example of pile driving innovation. That was funny and pretty cool. Okay, thanks for watching. See you in another video.